Hey class, I'm really bummed about the snow day today. We don't get together to have physics, but physics must go on since it's physics of everyday life. So I figured I would talk to you a little bit about rockets and space travel and using the physics that we've learned so far to understand a little bit of the kind of principles behind rocket travel. We won't get into all the complexities of how rockets work and so on, but thought we should at least learn a little bit about it. So if you remember at the end of last class, I gave you these 6 questions to think about and consider, and we're going to talk about some of them here today and probably finish up the rest of them on Friday when we have class together. So I want you to take a minute and think about how you would explain the answers to these questions using physics. Maybe pause the video for a minute or talk to your roommate or your friend or your pet cat or whatever it is that you have near you and think about how physics can explain the answers to these questions. All right, so hopefully you paused and thought about it. So the first question is, what moves a rocket forward? So there's a lot of ways to answer this question. Some of you might say, well, it's, the fuel. True, but how? What physics are at play in using that fuel to propel the rocket ship up or forward in the direction it's desiring to go? And the answer is that it is about the gas, but it's not just about the fuel. It's the fact that it's throwing or pushing the fuel out the back of the rocket. That pushing out in the backwards direction leads to a momentum in the upward direction for the ship because of conservation of momentum. If you think about it, the total rocket and fuel together have an initial momentum of 0. They're both stationary when they first start. Once the gases ignite, the fuel gets thrown out the back with a velocity in the downward direction, meaning its momentum would also be in the downward direction. That would give then the rocket ship momentum in the opposite direction, upward, to keep the conservation of momentum still 0. So thinking about this again, since momentum is going to be redistributed between the two, the fuel is thrown backwards with momentum in what we could call the negative or backwards direction, and due to conservation of momentum, there must be an equal and opposite momentum on the rocket in the forward direction, again as a result of conservation of momentum. And so it's this momentum forward that propels the rocket. And you can also think of it in terms of Newton's third law is another way a lot of people kind of conceptualize rocket travel. Since there's a force out the back to eject the fuel, there must be an equal and opposite force forward on the rocket. And that's why rockets need such an immense amount of fuel, because the forces are equal and opposite. So since you just have lightweight gas being thrown out the back, you need a lot of it to propel that heavy rocket ship in the forward direction. So again, the total momentum started at 0, and since it's more or less an isolated system, the final momentum would still remain 0 for ignoring friction and other air resistance outside forces. All right, so again, to look at this in terms of equations, since we want to kind of keep in mind how we quantify these things with equations, we know that the initial momentum is going to be equal to the final momentum, conservation of momentum, right? So that means that since our initial momentum, everything's at rest. Again, what is momentum? Mass multiplied by velocity, right? So the initial velocity of everything is 0, so its initial momentum is 0. So that will just be equal to the final momentum of the fuel plus the final momentum of the ship. And so we can go ahead and do a little bit of algebra, and we see here moving our momentum of the ship to the other side of the equation by subtracting it from both sides. We get negative momentum of the ship equals the momentum of the fuel, and since we know mass times velocity is equal to momentum, I flip my negative side sign to the opposite side, and I get mass of the fuel times the velocity of the fuel equals the momentum of the ship, which again we could have substituted in, that's the mass of the ship multiplied by the speed of the ship. But what you see here is in order to get your ship going fast and forward, to give it a lot of momentum, you must have a large mass of fuel being shot out at very high speeds. So those are the two main contributing factors to determine how fast your ship can get going, is how much mass you have of your fuel and how much speed that fuel is able to be ejected out the back of the rocket. So if you remember back to our introductory question that we ended with last time, If there's no launch pad, how would the liftoff compare? We concluded that it would be about the same, and this is why, right? That launch pad doesn't play into effect with the momentum whatsoever. And so removing it, you still have conservation of momentum being used to propel your spaceship in the forward direction. It's a little more complex than that, and it could affect things a little bit, but with the big picture physics applications, it's really not going to have a significant impact. So, next question. How does the rocket use that gas to obtain its thrust? Well, some of you might already answer, well, by momentum, right? As we just talked about. But let's look at that a little bit deeper. Yes, it is conservation of momentum, so it's shooting the gas fuel out the back that propels your rocket ship forward. But let's look at the physics at play there in a little greater detail. So what happens is these engines not only eject the gas, but first of all, they have to burn the fuel, and so they are using its chemical potential energy, turning it into really ultimately kinetic energy, energy of motion. They heat it up, make it really hot, and that heat makes it want to move faster, and so those gas particles are moving really fast, and then they get shot out the back of the jet engine. And those engines or thrusters then also need to not only burn the fuel and heat it up, but also redirect it so it shoots out the back of the engine. So you heat it, get it moving real fast. That's a result of combustion, using the chemical potential energy through burning, not dissimilar from burning a log that produces heat in your home and so on. But that combustion makes it very hot, and because it's all close together in a tight area, it gets high pressure as well, and that makes it want to really shoot out or move fast with a lot of momentum. But if you just had a cylinder and you're just burning the gas in the cylinder, kind of like you see here, what's going to happen is your fuel that goes shooting out is going to be bouncing all over the place and flying in all different directions, kind of like this, right? And any little arrow not pointed straight back, pointed off to the sides at all, is going to result in wasted momentum. Because if you have momentum pointing upward and momentum pointing downward, this is a great picture, here we go, anyway. So if you have momentum pointing in two different directions, they're going to be working against each other and cancel each other out, and you're going to have wasted momentum. So you really want this gas not to be coming out in all random directions like you see in my picture here, but rather you want it all to be as uniform as possible. Do any of you know how we can create that gas exit in a much more uniform direction? What engineers and astrophysicists and so on, well, not really astrophysicists, mostly aeronautical engineers and aerospace engineers. Anyway, what have they done to try to make the direction of this gas more uniform? Any ideas? Well, some of you might know, but they use something known as a de Laval nozzle. They take this nozzle, pop it on the back, and because of its structure, it's actually able to funnel the gas and then allow it to expand out. And the curvature of the nozzle here, this curvature here, is just right so that when it redirects any fuel that's bouncing around in crazy directions, it redirects it to come straight out the back of the nozzle in a real uniform linear manner. So the de Laval nozzle is able to kind of constrict the gas, which results in it speeding up a little bit, added bonus, all right? And then after it speeds up to these really, really high speeds, supersonic speeds at times, supersonic meaning faster than the speed of sound, but those high speeds is part of why, if you remember from the video we watched, why the rocket was so loud. It's because of those high speed gases. So they speed it up, but then almost more importantly, I would say, is the way that they redirect the gas so that it all comes out more or less straight and you're not wasting momentum with gas particles bouncing off to the sides. So this nozzle redirects the gas, sending it straight out the back in a much more uniform manner. All right, so next question. What keeps the rocket pointing forward? And we actually touched on this a little bit on Friday, but how do rockets control their direction? Question, this one, it actually depends a little bit, all right? Because rockets are made to travel both through Earth's atmosphere and out in space. And so the answer to this question depends on where you're at. If you're in Earth's atmosphere, what is used? Any ideas? Well, it's aerodynamics. You use the air in the atmosphere, not dissimilar from an airplane wing and so on that we'll talk about in Chapter 6, okay? But it uses air, deflecting and pushing off the air to control the way that it flies not, again, dissimilar from an airplane or even like a frisbee disc that you throw or something like that. When you're out in space, though, the aero part of aerodynamics doesn't work very well since there's not much air whatsoever. So when you're out in space, then you have to use something different. And so when you're out in space, it uses those little, excuse me, those little thrusters on the side of the rocket that you've probably seen in science fiction movies and so on. There's these little, oh, sorry, that's my dog Gus. He's excited about physics too. Who can blame him? Or an animal in the backyard. Anyway, there's little thrusters that shoot off the sides, and those can offer little forces at distances away from the center of mass of the rocket that generates a torque, and that torque can cause it to rotate. Just to kind of make sure you understand what I mean here, I can show you on the board. Here's my wife's favorite animal is the mola mola. It's the ocean sunfish. It's this little one that she drew for us to be enjoying physics class with you as well. Anyway, so if you have your rocket ship, okay, that's a beautiful rocket. You know, you got your thrusters down here. Oh, I didn't draw the De La Velle nozzle. Whoops. So anyway, you got your thrusters down here with your nozzles. Okay, this is a beautiful drawing, obviously. You got the gas shooting out the back. Say that your center of mass is somewhere in this region, all right? Now, if you want your rocket to turn when you're out in space, if you want to turn right, you could have a little thruster right here, shoot gas out this way. Equal and opposite, there'd be a force on the ship in this direction. That's some distance, a lever arm distance away, we can call it R, from our center of mass. And so there would be a torque generated that would cause it to rotate to the right. And then you'd be able to then, as a result, turn your ship to the right. So that's part of how these rocket ships are able to control the direction they're able to move, is by generating a small force with these little thrusters to rotate your object as a result of the torque that's generated from that force. Pretty cool, right? Physics rules. So that's how they adjust their direction. So my next question to you all is, what is a spaceship's speed limit? Like what, let me rephrase maybe a little bit. What determines or what affects how fast these ships can get going? My guess is some of you can probably figure out or make some guesses based on what we talked about earlier, but it has a lot to do with how much fuel you have, how fast that fuel can be shot out, but it also is dependent on your spaceship, right? The bigger ship is going to need more fuel, more momentum to get going because it has more mass. So it depends on the rocket fuel mass and the spaceship mass. So let me kind of walk you through this a little bit more. So the spaceship's speed is going to increase if you have more mass of fuel compared to the mass of the ship, and it's also going to increase if your fuel is able to be shot out at a higher speed, which makes sense from conservation of momentum, right? If we use the conservation of momentum equation earlier and added in mass of the ship times the velocity of the ship for its momentum, as you see here, and I divided the mass of the ship over, this is what you would get just using conservation of momentum. Now this is a nice equation, and it gives us an idea of how these things relate. More mass of fuel, more velocity of the fuel, faster our ship can go. Less mass of the ship, because it's on bottom, the faster it can go as well. But this equation is actually not super accurate, because what happens is as you're propelling your ship upwards, guess what? You're using some of the fuel. And the overall ship and fuel together that you're trying to move is getting lighter. Every instant that you move up, it's a little bit lighter than it was before. And so this is not really an accurate equation to determine a final velocity. Instead, you'd have to use some fun calculus, some integration, and so on to derive a more general equation for the final velocity of a ship. Instead of making you all do a bunch of calculus, though, I figured I would just go ahead and tell you the result. So this is the resulting equation. It looks a little bit large and burdensome, but don't fear, it's really relatively straightforward. What it tells us is that the velocity of a ship, the maximum speed that it's able to reach, is going to be equal to negative. The reason that the negatives here, again, don't get confused, the negative just means the velocity of the ship is going to be in the opposite direction of the velocity of your fuel. Okay, so negative ln Anybody know what that means? Natural log, okay? So that's just a button on your calculator, the natural log button. So negative natural log of the mass of the ship plus the mass of the fuel, so the total mass of your initial payload, everything together, divided by the mass of the ship. So this is really just a ratio, actually, of how much mass is in which category, multiplied by the velocity of the fuel. All right? So let's go ahead and do kind of a sample calculation here. Typical fuel velocities, they're able to be ejected at somewhere in the ballpark actually of like 10,000 miles an hour, which is about 4,500 meters per second. In order to get into Earth's orbit and escape kind of the main gravitational well of the Earth's surface, we want our ships to get up to speeds in the ballpark of, let's say, 10,000 meters per second, almost 22,000 miles an hour. All right, so to go to infinity and beyond, to get up to this speed or above of 10,000 meters per second for our ship, what ratio of mass to fuel do you think we need? Let's do some examples. Let's try it together. What if there was 50% of the fuel was ship and 50% was, 50% of the total mass was ship and 50% of the total mass was fuel? What if 75% of the total mass was fuel and 25% was ship? What if 90% was fuel and 10% was ship? I want to try to use this equation with the numbers given to see which of those ratios can actually get us to the escape velocity, get us above this 10,000 meters per second. So I want to try this together. Go ahead, pause the video. I'm going to actually pause it too and erase the whiteboard behind me. And I want you all to try this out, and then we'll tackle it together. All right, so hopefully you all have given that problem an attempt. Let's go ahead and jump in together on my whiteboard here. All right, so I wrote down my equation. The velocity of the ship, how fast it's able to achieve its maximum possible speed, again, is equal to the negative natural log of the mass of the ship plus the mass of the fuel, so that's our total overall mass, divided by the percentage or the mass of the ship, and then multiplied by the final velocity. So this is a little bit tricky, right? Because we're given the fuel velocity. Sorry, this is not final velocity, that's the fuel velocity. I misspoke. Fuel. So we know the fuel velocity is 4,500 meters per second, and we want the velocity of the ship. But the question is, what about the mass? I didn't give you any masses. All I said was, what if it's 50% fuel or 75% fuel or 90% fuel, right? Well, check it out. What we can do, since these are divided, this is really just a ratio. So if they're 50-50, we can kind of make up numbers, all right? If it's 50% for each one, let's just use mass of the ship. Let's call that 50 units. And the mass of the fuel would also be 50 units. So if we plugged that into our equation, then the speed of our ship would be equal to negative natural log 50 plus 50, so 100, divided by 50, multiplied by 4,500 meters per second. So 50 plus 50 is 100, divided by 50 is 100 over 50 is just 2. So this here is just the natural log of 2. So our velocity of our ship would be equal to negative natural log of 2, then multiplied by 4,500 meters per second. And the natural log of 2, if you were to plug that into your calculator, comes out to be equal to 0.69 approximately. And so we take 0.69 to multiply that by 4,500 meters per second to figure out the speed that the ship can achieve. And so what this is saying is that our ship can only get up to about 69% of the speed of the fuel. Not that fast. If we did the math here, we would get negative, let's see, 3,120 meters per second is the speed that our ship could achieve. Not nearly fast enough to get into orbit, because we wanted, again, remember 10,000 meters per second. So 50-50, not even close. We could probably get up high in the Earth's atmosphere, but that's about it. So now we have to go back and try again. Oh boy, howdy. So I erase all of this. Now everything else stays the same, but we're changing our mass ratio, right? So again, now we're looking at 75% fuel and 25% mass of the ship. So again, you could do 25 and 75. I'm going to do it a little differently because there's multiple ways to do this. All right, let's say 25 and 75 is the same as the fuel being 3/4, so 3 units, while the ship is just 1 unit. That could be the same exact answer as if you did 25 and 75. So let's use those. Our ship is going to be able to reach a speed of negative natural log. 1 plus 3 is 4, divided by the ship, which is just 1, multiplied by then the 4,500 meters per second. So now here what we see is the speed of the ship is going to be equal to a negative natural log of 4 multiplied by the 4,500 meters per second. So the natural log of 4, I popped it out of my calculator also. It comes out to be equal to 1.39. So now we can achieve a speed 139% of the speed of the ship, or excuse me, of the fuel. So the negative 1.39, again, that's the natural log of 4. Multiply that by 4,500 meters per second. And now our ship can get up to a speed of a negative 6,240 meters per second. Getting fast, but not fast enough to escape Earth's gravitational pull. And again, keeping in mind, don't forget, why are these negative signs here? These negative signs just mean that it's moving in the opposite direction of the fuel. So if it's shooting the fuel down, the ship is going up. All right, let's do our last trial here and look at what happens if you have 90% fuel and only 10% ship. So I'm going to go ahead and leave 1 unit for the ship, and that would leave 9 units for the fuel. We're going to do the same thing. Oh, Gus is really excited about rockets. Gus, a good boy, bud. Sorry. He sounds like a tough guy, but he's really a teddy bear. All right, so the velocity of the ship is going to be negative natural log, again, ship plus fuel. 1 plus 9 is 10, divided by the ship, which is 1, and then multiplied by the 4,500 meters per second. So now we're doing natural log of 10. So the ship is going to equal negative natural log of 10 is here 2.30. So we're getting even faster. Multiply that by the 4,500 meters per second, and the velocity that our ship can achieve is going to equal a negative 10,360 meters per second. Cool, that's box worthy. We now have been able to go to infinity and beyond, in the words of Buzz Lightyear. So only once we had 90% of our overall mass dedicated just to fuel were we able to actually escape the gravitational pull of the Earth. So it really takes an immense amount of fuel to be able to escape out of Earth's gravitational pull. So there's Buzz Lightyear for you guys. All right, so I think I'm going to go ahead and stop here. We're going to pick up with questions 5 and 6 on Friday. So we're going to talk about weight in space and how weight changes depending on your location, as well as Kepler's laws of motion. But for now, I think we're going to call this good. So make sure you check this out. And if you have any questions whatsoever, let me know and come on Friday prepared to pick up from here. Have yourselves a box-worthy day.